All right, welcome linear algebra students. This is Mr. Margraff. I'm sorry that I'm not with you today, but we're going to do the lesson this way. So if you will get out your notes and look at section 4.1, vector spaces. Vector spaces and subspaces. So the first definition in your handout is what a vector space is. So the handout says a vector space is just a non-empty set. So I'm going to say non-empty set. So a collection of objects. But it's a collection of objects with 10 special properties. So 10 properties. And we want, when we're checking to see if a space is a vector space, you want to see that these 10 properties are all satisfied. So let's go ahead and list them. What are they? The first one, the first property is called closure. So closure of addition. I'm going to put a little plus sign below it. And it says that if I take two things from the vector space, this, remember, means inside the vector space. So we'll let u and v be inside the vector space. Then it's the case that the sum of those two things also stays in the vector space. This is called closure of addition. So if two things start in the vector space, then their sum has to be in the vector space as well. Now this is a vector addition that's happening between u and v here. Okay, well, what's the next property? The second property is called commutativity. And what does it say? So it says if we take two things from the vector space, let two things be inside V, then it's the case that u plus v is equal to v plus u. So that's called commutativity of addition. So, okay, well, what about the third property? The third property is associativity. So we'll say associativity. Okay, and this is again associativity of addition, and we'll let three things be in the vector space, u, v, and w. Then that means that u plus v plus w is the same thing as u plus v plus w. So the order of our addition makes no difference inside of a vector space. This is something that has to be satisfied in order for something to be considered a vector space. The next property is called the additive identity. So we want additive identity, so we'll say identity. And put a plus sign below it. So what does it say? That means that there has to be, I'm going to say there is a vector, we'll call it the zero vector inside V, so that 0 plus u is equal to u plus 0, which these are the 0 vector, is equal to u. So what that means is there's a vector inside the space that no matter what vector you add it to, it's going to give you the vector itself. So it identifies, it tells you what you're dealing with. So it leaves everything else alone. In this vector we call the 0 vector. So that's the additivity of addition, or excuse me, the identity of addition. Okay, well, the next one, we want an additive inverse. So this is called the inverse of addition. And so that means we'll let u be inside the vector space V, then there is a vector, you could say V in the vector space V, so that u plus v gives you the 0 vector. But typically we don't write v like this. We just say v is minus u. So there has to be a vector out there that undoes u. So that means when I add u to minus u, I'm going to get that identity, or the identity vector, 0 vector. So there exists some vector out there that does that to u. So that happens for every vector. So for every vector, there is an additive inverse. Okay, well, there are 5 more properties. These are scalar multiplication properties. So these here, the first one is closure. And I'm going to say for multiplication, I'm going to put a little times sign down there. So we'll say let U be in the vector space V, and we'll let C be any scalar. Then C times U, so we're scaling the vector U by C, has to stay inside the vector space. So it does not leave. You can stretch vectors and they stay in the vector space. Well, the next property is scalar distribution. So we want, we'll let U and V be in a vector space, V and C be a scalar. Then we want U plus V times our scalar is the same thing as CU plus CV. So this is scalar distribution. Now, these properties may seem a little trivial, where it's like, well, duh, we've been doing this all along. But here, we're talking about the structure of this space. So of what is a vector space? We're defining a vector space. So all vector spaces have to have this property. If they don't, then it's not a vector space. So it has to have this property that you can distribute scalars over multiplication. The next one is vector distribution over a sum of scalars. So I'm going to say vector distribution. So it's going to look like this. We want to choose 2 scalars this time. So we'll let C and D both be scalars. Then C plus D times a vector U is the same thing as CU plus DU. Which again feels very intuitive, but it's something that needs to be stated here for a vector space to actually be a vector space. So we have to be able to add scalars and then stretch that vector U by the sum of scalars, or you could just stretch each one and then add the stretches together. Okay, well, the next property is associativity under scalar multiplication. So we want associativity. For multiplication. So what does that look like? We want to take 2 scalars, so let C and D be 2 scalars. We don't want that to be in the vector space, so we'll call those scalars. And then U in the vector space V. Okay, so now let's scale the vector U by D, and then scale that by C. So now this is the same thing as scaling by the product of CD. So this is associativity of scalar multiplication. So it doesn't matter if I scale by D first and then U, or then by C. It doesn't really matter. You could even say here that this is, since we know that real numbers are associative in their properties, we could say that D times C is U, and then you could bring that D out. So scalar multiplication is the same here. Okay, well, the last property, the 10th property, has to do with multiplication again, and it's like what we've seen up above here for the identity of a vector space here for addition, but we want the identity of scalar multiplication. So we'll say identity, and I'm going to put a little multiplication down here, and so we want 1. So there is a scalar. 1 is the real number 1. And then we'll let u be in the vector space V. Then if we scale that vector u by 1, it just gives me u. So no scaling has happened. It identifies the vector u as itself. So this is the scalar identity for multiplication. Now all 10 of these properties are on the next page here in your notes. So let me just kind of highlight some keys here. Notice that this is a non-empty set. A vector space is a non-empty set of objects, and we call those objects vectors. And they have to have two binary operations. The first called addition, and the second multiplication by scalars only. So you can't multiply vectors. We don't really have not for a vector space yet, we don't have a definition what it means to multiply vectors. So we only have scalar multiplication at this point. But we have these 10 axioms or properties for our vector space. Now, it's the case that we can simplify a few of these or deduce some new things from these in this next note here. So notice that if I scale a vector by the real number 0, so scaling by 0, we get the 0 vector, so 0 vector. These two zeros here and here are not the same 0. The 0 on the right, I tried to make it bold, we can see that it is the vector 0, and the 0 on the left is the scalar 0. Now here, what if we try to scale the 0 vector by c, so scaling the 0 vector? Well, when you scale the 0 vector, you still get the 0 vector. So nothing about that changes. And you might have felt a little bit of kind of an annoyance when we did the additive identity here. You might have said, well, what was the purpose of doing that? Minus u. Isn't that just subtraction? And so subtraction is not really one of the properties of our vector space, but here we can view this additive inverse as the product of or the scaling by -1. So I'm going to say additive inverse is scaling by -1. Okay, so that's the same thing, and when I'm adding the additive inverse, it's the same thing as really just subtraction, is what we know it. But it's really an additive inverse, or scaling by -1. Let's look at a few examples of some vector spaces here. So on the next page, this above example 1, here we have a number of vector spaces here which follow all 10 axioms. So the first one here is what we studied in multivariable, is just Rn. So this is probably one of the most trivial or the most obvious vector spaces. What we've been dealing with in multivariable calculus is just the space of n-tuples or vectors from Rn. And these are just vectors that are n-dimensional vectors. So like we've been doing 3-dimensional vectors, you could have an n-dimensional vector, and you can add these together, you can subtract them, you can scale them. So these have all 10 properties that we were talking about, and we've been using these throughout this course so far. So there's nothing surprising about that being a vector space. But what might be more interesting is this next bullet point here, is that a vector space of just these abstract objects, just of arrows. So arrows in 3 space. So your vector space is arrows, and you can add arrows together by the parallelogram rule, which we've learned. That's kind of abstract, but you can add them together. You can scale them, so we can still scale these arrows by stretching them and keep their same direction. And we can say that vector vectors are equal, or arrows are equal if they have the same length and direction. But this forms a vector space that has all 10 properties that we were talking about on the previous page. Even more abstract might be the space of all doubly infinite sequences of numbers. So what does it mean to be doubly infinite? Well, that means a sequence that goes off in both directions. So you know a few of those. For example, just the integers would be a set of doubly infinite numbers. Okay, let's look at another kind of abstract vector space. In example 2 here, it says, let V be the set of all real valued functions on a set D, where D is just a set of real numbers. It says on some, so on some interval of R. That's, it says or, it should be on some interval of R. So we're taking all possible functions on some real set of numbers. So maybe it's, it doesn't specify, but maybe it's the numbers 1 to 2, and we're taking all possible functions just on the interval from 1 to 2 or something like that. And we're putting them in a bag, and we're calling that V. It's a set of functions. Let's take two functions out of this set. So we'll let f and g both be functions in this set V, and then we'll add them together in the usual way. So we'll take f plus g of t. So t lives in the interval d in the domain, and this is really just the same addition of f of t plus g of t, the usual addition that we're used to, real function addition that we've been using through algebra and calculus. So if we do that, and maybe we'll let c be a scalar, and then CF of t will define to be just c times f of t, the usual scaling of a function that we've used before. So with these two, this addition and scalar multiplication, the set V of functions, we'll say of functions, on D is a vector space, where its vectors are not the vectors that we're used to seeing, but vectors that are functions. It's quite abstract. It's definitely different. Okay, we can't do example 3 yet until we look back at the definition of what a subspace is. So we'll go back and read that. It's a definition on the previous page. Let's go find that. So here's definition 412. It says a subspace of a vector space V is just a subset H of V that has 3 properties. So instead of having all 10 properties that a vector space has, a subspace inherits 3 of those. As long as it has 3, then we know it's still a vector space. It can be shown that a subspace, as long as it has these 3 properties, is still a vector space. And the first one is that the subset has to have the 0 vector. So the 0 vector is in the subset H. And sometimes we say that H is non-empty, so we have to show that there's something in H before we can say that it's a subspace. So sometimes we just write H is not the empty set, so we just give empty curly braces there. The next property is that H has to be closed under vector addition. Let me just remind you of what that is. So if we have U and let's just say U and V in H, then U plus V is still in the subspace, or is in the subset. Okay, so as long as vector addition doesn't cause it to leave the subset, then it's okay. The next one is part C. It says that H is closed under scalar multiplication. So what does that mean? If U happens to be in H, then that means if I scale U, C times U, it has to stay inside H for all C. So for all scalars C. So C is a scalar. Okay, well now let's go see if we can do the next example, example 3. So we know what a subspace is. A subspace has to have those 3 properties. It has to be non-empty. Usually that just means we'll show that the 0 vector is in the subset, and it has to be closed under vector addition and closed under scalar multiplication. So as long as it has those 3, we know it's a subspace. So example 3 says, the set containing only the 0 vector from a vector space V is a subspace of V. It's albeit a very trivial subspace, but it's still a subspace. So let's actually prove that or show that that's the case. So we'll say since V is a vector space, then that means that property of the vector space means that there has to be a 0 vector. Then there is a 0 vector in the subspace. Remember, that was one of the 10 properties. The identity has to be in there. So then there has to be the 0 vector in there. Okay, and then we'll say let H equal the set containing only that 0 vector. Okay, now our goal is to show that H is a subspace. And the first thing is H is not equal to, maybe I should say part A. So let's say that. So part A, we'll say part A, H is not the empty set since the 0 vector is in H. Okay, so we know that there's something in there, so we've shown that it's non-empty. That's how we defined H, is that it has just the 0 vector. So we know that H is non-empty. Now the next thing that we have to do is choose 2 things out of H and show that when we add them together, they don't leave H. Well, if I choose 2 things in H, well, there's only one thing in H to choose. So we'll take, if I take the 2 elements that are in H, I still get the 0 vector. So the 0 vector added to itself, this is the identity property of addition. It leaves the 0 vector alone, and that is still in H. So this is closure under addition. Okay, well now let's look at the last part. So the last part, part C, we want to show that it's closed under scalar multiplication. So we'll let C be any scalar. Choose any number you want, so C can be 10, 5, or whatever, and we can multiply it to the 0 vector. So 5 times 0, whoops, I confused myself there. I want C times 0 is still the 0 vector. That's a property in our note that we had on the previous page. Remember, if you just scale, if you scale 0, it stays 0. And so by scaling the 0 vector, this happens to stay inside H. It does not leave. So that means that this is closed under scalar multiplication. Cool. So this means that H is a subspace. So we'll say H is a subspace of V, and usually what we write, I'll say we write H is a subspace of V. We use a less than or equal to, showing that H is contained in V. So a subset, I don't know if I've showed this to you before, but a subset looks something like this. So this means subset. And this notation here means subspace. So it's almost like an abusive notation, so subspace. Because the less than or equal to symbol already represents something. It means that like 1, we would say 1 is less than 5, less than or equal to 5. But here we're saying h is less than or equal to v. So we have to use context clues to kind of help us determine what this symbol means. That symbol tells me that h is a subspace of v. Okay, good. So now we can actually say that any vector space has to have a subspace, and it's this trivial subspace called just the zero vector. That's all it has in it, is just the zero vector, and that is always going to be a subspace of any vector space. Okay, well, let's look at the next page here. So we have already seen that the set of all functions on a domain form a vector space. And we've also seen that the nth degree polynomials form a vector space. And so the set of all nth degree polynomials, p sub n, that we saw before in example, I think it was example 1, is actually a subspace of the vector space of all real valued functions. So all possible functions, and you just take this small subspace of them, which is the set of all nth degree polynomials, and that's a subspace. Okay, well, let's have a look at example 5 here. It says, is R2 a subspace of R3? And it says, is the set, here they give us a vector of R3, where S and T are just real numbers, and the third component of this vector is 0. They ask, is that a subspace of R3? Well, let's tackle the first one here. Is R2 a subspace of R3? Well, coming from multivariable, we would almost instinctively say, yes, it is. But you might be a little too hasty there. Let's look at vectors in R2. So vectors from R2 look something like this, A and B. So this is in R2. Okay, and so then what do vectors from R3 look like? They look like maybe something like this. So I'm never going to come across a two-dimensional vector inside a three-dimensional space. You'll always have a three-dimensional vector in a three-dimensional space and a two-dimensional vector in a two-dimensional space. So you're not going to have, you can't somehow get that third component there that we're lacking. So the answer is no, this is not a subspace. So we'll say no, R2 is not a subspace of R3. It seems like it would be, but it's not. Let's attack the next one. It says, is the set H, S, T, and 0, is that a subspace of R3? Well, the vector is certainly the right size, so I'm going to say correct size. So the problem where this failed over here was that there are no vectors in R2 that are in R3. So R2 is not even a subset of R3. So it doesn't even contain any of the same vectors. So we can't say that it's even a subspace. But here, in this next one, H is at least the same size as R3. So now the question, is it a subspace? Well, let's go through the three properties. Is H non-empty? Well, let S and T equal 0. Then the 0 vector is in H, and H is non-empty. Okay, so we've done part A. So it's almost a subspace, so we have to look at what it means to be a subspace. So what if I add two vectors, S and T together, so something like this. If I add A, B, 0 plus C, D, 0, that's going to give me A plus C and B plus D, 0, which is still in H. A plus C can be S, and B plus D can be T. So this is still in H. So it's closed under addition. And what if I scale it? So let's choose some new letters here. What if I choose R? And here we have S and T, and I scale by the letter R. That's going to give me RS and RT. And that is still in H. I can choose S to be RS and T to be RT, and that's still in H. So it's closed underneath scalar multiplication, and it's closed under vector addition. So that tells me that this H is a subspace of R3. So the answer is yes for that one. So yes. If we look at example 6 here, it says, is a plane in R3 a subspace of R3, and is a line in R2 a subspace of R2? You might be kind of anticipating a trap here. So the answer is not always for each one of these, and so we want to maybe describe when it is the case that a plane of R3 is a subspace of R3. So we'll say not always. Then I'm going to say a plane containing the origin. Containing the origin is a subspace of R3. Why does it have to have the origin? Well, remember, one of the properties of a vector space is that it must contain an identity element, that when an additive identity, that when you add it to anything else, it leaves it alone. And if a plane in R3 doesn't go through the center or the origin, then it's not going to contain the zero vector. If it doesn't contain the zero vector, it has no additive identity, and therefore it's not a vector space. Same thing for R2. So R2's so we'll say not always. So we'll give another reason here. A line must contain the origin. Notice, let's take this moment to go back to example 5, and notice that this last element there is 0. If that hadn't been the case, say it were something like 5 or something there, then we never would have been able to do this. We never would have been able to say that the 0 vector happened to be in H, namely that the subspace is, or the subset is non-empty. So if we couldn't have said that, then there's no hope. There would have been no hope of the 0 vector being in there. So it was kind of crucial that this last element there was the just 0. All right, well, let's look at example 7 and see what it says. It says, given v1 and v2 and v, let h equal the span of v1 and v2, and we want to show that the span of two vectors from a vector space is actually a subspace of v. Okay, well, we have to go through the three properties. So let's start by showing that the 0 vector is in the span, and we might want to remind ourselves what the span actually is. So let's maybe start by, I'm going to say a little proof here. We'll say let v1 and v2 be inside of v. They technically said that for us, but I'm going to restate it just to be clear. And then we'll say let h equal the span of these two vectors that we pulled out, v1 and v2. And the span is really just the collection of c v1, the scaling of v1, plus the scaling of v2, c v1, plus dv2. So we're scaling all possible scales of v1 plus all possible scales of v2, where c and d are just real numbers. That's what it means to span. So the span is all possible, the sums of these two vectors. Okay, all possible linear combinations, to use the vocabulary that we have used previously. Okay, now we want to show that h here is a subspace of the original space V. So, well, so for part A, we want to show that the 0 vector is in H. So I'm going to say choose C and D to be equal to 0. Then 0v1 plus 0v2 is actually equal to the 0 vector, which is in H. Okay, so we have found a linear combination of V1 and V2 that is still in H that gives me that additive identity. So I've found the 0 vector. Okay, very good. So H, we can say here, is non-empty. Cool. All right, so part A is good. So now let's do part B. Part B, what does it say? So part B says you have to take two vectors out of H and show that when you add them together, they stay in H. So I'm going to choose, so we'll we'll have to pick two new vectors. I'm going to call them H1 and H2 in H. Okay, now remember, you have to choose them out of the subset, out of H. So we're choosing them out of there, and we want to add them together and show that they stay there. So I'm going to maybe even put this here. We want to show that H1 plus H2 is still in H. We want to show that it's closed under addition, that it doesn't leave the subset when you add them together. Okay, well, first of all, let's use the property that H1 is the span of V1 and V2. Since it's in H, it has to be the span of V1 and V2. So we'll say there exists, or we can say there are scalars. Let's see, what do I want to call them? I'm going to call them C1 and C2, and then we'll say D1 and D2. These are just real numbers, so H1 is really the span of V1 and is in the span of V1 and V2. So H1 is really just C1 V1 plus C2 V2. Remember, it's in the span, okay? And H2 is equal to D1 V1 plus D2 V2. So it's still in the span as well. Remember, it's H1 and H2 are from H, so that means that they have to be a linear combination of V1 and V2. Okay, so now why did I go through that? Let's add them together and see what happens. So we want to consider H1 plus H2. That's going to be C1V1 plus C2V2 plus D1V1 plus D2V2, which means that I can just add or combine like terms here. So let's combine my V1s and combine my V2s. So the new coefficient of V1 is C1 plus D1, V1. C2 plus V2, that's a D2, V2. And notice that this is still in the span of V1 and V2, which is the same thing as H. So notice, all the way over here on the left, this is H1 plus H2, which is what we were wanting to show, is in H. So we're showing that it's in H. Wow, so this whole time, I just chose two random things, H1 and H2 out of H, and it just so happens that the sum of those two things stays in the subset. Okay, well, let's try the last bit here. This is part C. It's going to be very similar to what we just did. We want to choose a scalar, so I'm going to let, it looks like C is kind of in use here, but let's maybe say let C3 be a scalar. And then we'll scale a vector from H. So we'll let H3 be in H, and then we know there are new scalars. We're going to call them E1 and E2. This is getting a little bit boogery. Maybe I should go back and use. Let's just, if you will permit me, I'm going to go back and use H1. So H1. Remember, H1 is really just C1V1 plus D1V2 or D2V2. Whoops, I've said that wrong. C2V2. There we go. C2V2. Okay, so now let's scale H1 by C3. So then C3 H1 is really just going to be C3 times, let's replace H1 with what we know it's equal to. That's going to be C1V1 plus C2V2. And this is just going to be C3C1 V1 plus C3 C2 V2, which is still in H. So this is still in, maybe I'll connect it one more time. So this is still the span, in the span of V1 and V2, which means that it's still in H. So therefore, we can finally say the span of two vectors from a vector space, the span of V1 and V2 from some vector space V is a subspace of V. So this is a subspace. All right, we'll put a little box there to show that we're done with our proof. Very good, cool. That was tough. That one was kind of tough. That might be a good one to rework and do on your own, and just kind of maybe choose your own letters and stuff. Like, did I have to choose C1 and C2, D1, D2? No, of course not. You could even choose new letters, C, D, E, F, or something if you wanted, but that might get a little confusing. But it's already confusing. So hopefully that made some sense there. But we want to. Our goal is to show that it's closed under scalar multiplication and closed under vector addition. Okay, let's look at example 8 next. It says let H be the set of vectors of this form. So we have A and B here, and A and B are just real numbers. They say show that H is a subspace of R4. Well, the first thing that you might want to do is show that it's non-empty or that it has the 0 vector. So I'm going to say here choose. What do we want to choose A and B to be? So A and B, we want to choose them equal to, maybe if we are looking for the 0 vector to be in this subspace, then I'm going to say choose A and B equal to 0. But I actually just now we could go through it directly and show part A like we just did. But I actually just made a realization here. If you look very carefully at this vector, that it is in kind of a form that that we might be familiar with. So let's actually write out the vector A minus 3B, B minus A. A, B. So we could go through it directly. This is direct. But I'm about ready to show kind of an indirect way of showing that it's a subspace. But this is equal to, I'm going to say A times the vector. Let's see, the coefficient of A is 1, negative 1, 1, and then 0, plus this is going to be B times the coefficients of B are negative 3, 1, 0, and 1. And so this is really the span of these two vectors, 1, negative 1, 1, and 0. And then this one is negative 3, 1, 0, and 1. And so the span we know from the previous example, so I'm going to say by example 7, here, we know that this is really just a subspace of R4 because the span of two vectors chosen from the subspace is a subspace of the original, the span of those two vectors is a subspace of the original. So here, this method over here showing A, B, and then C is a direct method, which you could go through that and do that if you want, but that's kind of a pain. But here we have something a little bit more powerful. We see that by our previous example, which we proved that a subspace, the span of two vectors, is a subspace of the original vector space. Very cool. Let's look at our last example here, example 9. They say, for what values of h will y be in the subspace of R3 that is spanned by these three vectors? Okay, so we've got three vectors, v1, v2, v3, and y. We want to find out what value h will make it y a vector inside the span. Well, this is something that we've done before, so this should be some very familiar to us. We're just using some new vocabulary here where we want, we're looking for, we're kind of using this subspace vocabulary instead of, before we would just say what makes y, what puts y in the span of v1, v2, and v3. So what we are asking is this question here. It's just the same question as putting v1, v2, v3 augmented with the vector y. So we're augmenting these, and then we want to row reduce. So this is 1, -1, -2, 5, -4, -7, -3, 1, 0, and -4, 3, and h. Okay, now let's start our row reduction. So let's eliminate the -2 and the -1 there by adding multiples of row 1. So I'm going to add 1 of row 1 to row 2, and we get a 0 here. 5 plus -4 is a positive 1. -3 plus -1, or positive 1, is -2. And then -4 plus 3 is -1. Okay, and then now the last row down here, if I add 2 of the first row, it's going to be 0. 10 minus 7 is 3. -6 plus 0 is -6. And then 4. H plus 2 -4s, so that's going to be h minus 8 there. Okay, and now we want to continue our row reduction, because in order for in order for y to be in the span of these three vectors, we're looking for this system to be consistent. If the system's not consistent, then what that means is no possible linear combination of v1, v2, and v3 could ever give us y. So we're looking for it to be consistent so that we can find the multiple that gives us that last vector y. Okay, so let's eliminate that 3 below the second pivot element there. So we want to subtract 3 of row 2 from row 3. So I'm just copying the rows here. Okay, and so we'll subtract 1, 2, 3. So that means I'm going to get 0, 0 here. And I'm subtracting 3, -1, so it's going to be -8 plus 3, so it's going to be -5 there. So in order for this to be consistent, we want this last row, so that tells me that 0 has to equal h minus 5, or h must be 5. So this is the same kind of question that we've been answering before this section, but now we're putting it underneath the context of subspaces. So now we're looking for y to be in this. So y is in the span of v1, v2, v3, which is a subspace of R3. Yeah. All right. Good. All right. Well, this should be sufficient for completing your homework. But hopefully I will see you guys before too long. Thank you for listening.